take note that we've already introduced the idea of molar mass of an element, and of course that's the mass of 1 mole of atoms of this element. It is equivalent numerically to the average atomic mass on the periodic table, so you can always get the molar mass from the periodic table. It has the units grams per mole, and so when you look on the periodic table and you see that number there that corresponds to the mass, that is a mass of 1 mole of atoms of that particular element. Now, both the molar mass and the equivalency statement that's in the box in front of you can be used as conversion factors. And so I'm going to ask you to consider the key question number 1 that's coming up. Okay, so key question number 1 says, write Avogadro's number as 2 related conversion factors. Write the molar mass for nitrogen as 2 related conversion factors. So whenever you have an equivalency, you can use that equivalency as conversion factors. So I ask you to pause the video and give that a try right now. So for Avogadro's number, the conversion factor could be 6.022 times 10 to the 23 E particles per 1 mole of E particles. Now E in this case means elementary particles. I'm not specifying what they are, but if they were atoms, it would be 6.022 times 10 to the 23 atoms per 1 mole of atoms. Now we can write it like this, or we can also write it in the second fashion. Now mathematically you may think these are different numbers, but in a sense they're representing an equivalency, and it depends on what sort of conversion you want to do. Are you going from mole of elementary particles to particles, or vice versa? The kind of conversion you're doing will dictate the sort of conversion factor you need to use. In terms of molar mass, we can also come up with 2 conversion factors. So for instance, for nitrogen, 14.0067 grams per 1 mole of N atoms, or 1 mole of N atoms per 14.0067 grams. Note in this case I'm talking about atomic nitrogen and not molecular nitrogen, which had the formula N2. So what we're going to do in the rest of the activity is make use of Avogadro's number as well as the molar mass to see how we can make interconversions between actual number of elementary particles and the amount of material, and the amount of material and the molar mass. So let's take a look at the teaching model number 2, which gets us started. So in the teaching model number 2, we're going to see how we can use Avogadro's number as a conversion factor. In this case, we're asked to calculate the amount of substance, in the units of moles of course, corresponding to 3.011 times 10 to the 23 atoms of neon. Now I'm showing you all the work here, but I'd like you to see that there, in a sense, are some steps. For instance, it's really helpful, if it is obvious, to identify what the quantity is. So the quantity in this case happens to be the number of atoms of neon. We want to convert those number of atoms to the amount of substance. I make a unit plan and then identify the conversion factor that's necessary. Of course, in this conversion factor, in the numerator, it will be the mole of atoms. In the denominator, of course, it will be Avogadro's number. It'll be Avogadro's number that's canceled out with the corresponding units, and we'll end up with mole. Note that in terms of paying attention to sig figs, we end up with 4 sig figs. We started the quantity with 4 sig figs. It should not be Avogadro's number nor the molar mass that determines the final number of sig figs. You can think of Avogadro's number and the molar mass as being highly defined experimental quantities to the point that they're almost in a sense exact. So they will not define the number of significant figures. But that also points that you need to make sure that you use enough significant figures in your molar masses as well as Avogadro's number to do the appropriate calculation. So this is the prototype. I'm going to ask you to apply this to the key question number 2, which follows. So let's take a look. Key question number 2, I'm asking you to calculate the amount of substance from 1.00 times 10 to the 23 atoms of neon. So I encourage you to stop the video and just give this a try yourself. So as mentioned, there are some steps here. It's helpful to identify what the quantity is. and to realize you're going to change that quantity to a different quantity, in this case, the amount of substance. We're going to use a conversion factor to do this. In this case, it's the exact same conversion factor that was used before. After you've done this kind of work, either explicitly writing it down like this or in your head, as you will likely be doing later, it sets up the calculation so that it's almost foolproof. You don't really need to think too much about it, because then I'm going to write down what the quantity is, I'm going to multiply it by the conversion factor, and I end up with the final answer. Note that, as I would hope and expect, the units should cancel, so the number of atoms will cancel, and I'll end up with the amount of substance in moles. So that's an application of the model that we looked at. I'd like you to have additional practice. So exercises 1, 2, and 3 are very similar sorts of calculations. Once again, I encourage you to stop the video and give them a try, and then I'll go over each one of these exercises with you. So please give them a try. In this first exercise, it's almost exactly like the key question number 2, except in this case the quantity is a really small number, 1 atom, but it doesn't change the nature of the calculation. You're going to change the number of atoms to the amount, and it's the exact same conversion factor that we saw before. So it'll be 1 atom times the conversion factor will give us the final answer. Note that the number of atoms cancel, and we end up with the amount in moles. Be sure that you've done this calculation correctly, and that we should end up with a really tiny amount, 1.661 times 10 to the minus 24 mole of neon atoms. Very tiny amount, but of course we have a very small quantity of atoms. So almost exactly the same calculation that we saw just a few minutes ago. Let's look at the exercise number 2. In this case, we're starting with the amount, 0.25 mole, and we want to convert to the actual number of atoms. Be the amount, which is the quantity, 0.25 mole of neon atoms, and we're going to convert that to the number of atoms. We'll once again make use of Avogadro's number, but this time it's Avogadro's number in the numerator and the amount, 1 mole of neon atoms, in the denominator. When we do this calculation, it looks something like this, where the amount in moles gets canceled, and we end up with the number of neon atoms, 1.5 times 10 to the 23 neon atoms. It's helpful to step back and see, well, does this make sense? So we've got about a quarter mole of neon atoms. 1.5 is roughly a quarter of Avogadro's number. So yes, indeed, this calculation makes sense. And then finally, this time we're starting with an amount of neon atoms, but instead of calculating the number of atoms, we're asked to calculate the mass in grams. Now we do have a conversion factor for this, so we need to go look on the periodic table to see what the molar mass of neon is. So starting with this quantity, 0.25 mole, identify it, convert to mass in grams, look at the periodic table and find the molar mass of neon. Okay, so 20.1797 grams per 1 mole of neon atoms. When we do this calculation, 0.25 times the roughly 20 gives us 5 grams of neon gas. Again, this kind of makes sense. 1/4 mole of neon, and we end up with a mass that's roughly 1/4 of the molar mass. So here were 3 examples, exercises to practice this idea of a one-step conversion.